Greetings and welcome to 4th grade. This week we're going to cover operations and algebraic thinking along with number and operations in base 10. This is quite a lengthy lesson, so be patient. I tried to cover a wide variety of different questions, so there's a lot here. But let's get started with some operations and algebraic thinking. So with operations in algebraic thinking, we're still going to use the 4 operations: add, subtract, multiply, and divide, identify patterns, and then gain familiarity with factors and multiples. There are 2 snakes at the zoo, Jewel and Clyde. Jewel was 6 feet and Clyde was 8 feet. A year later, Jewel was 8 feet and Clyde was 10 feet. Which one grew more? Here on a number line, the top represents Jewel and the bottom represents Clyde. We can see that Jewel was 6 feet long if each one of these tick marks represents 1 foot, and Clyde was 8 feet long to start with. So then a year later, they each grew 2 feet. So I tack on the 2 feet here to each one. Additively, they both grew 2 more feet. However, we must compare how long they were before the 2 feet. We would compare what we call multiplicatively. So Jewel grew 2/6 of her length because the 2 feet, if we kind of place it above here, over the 6 feet in its length. However, Clyde only grew 2/8 of his length. So we can see overall that Jewel grew more. We have the following factor pairs of cards. Sort the cards into 4 different categories. Explain your thinking. Take a moment to kind of put them in order, how you think they should be put, and then we'll come back together and see how I did it. I'm going to put them in order based on what they actually multiply to. So 8 times 3 is 24, so I created a 24 category. 3 times 7 is 21, so I created a 21 category. 21 times 1 is also 21, so I can put that card in the 21 category. 12 times 2 is 24, so I'll put that in the 24 category. 13 times 1 will create a new category since that's 13. 6 times 6 is 36, another new category. 4 times 6 is 24, so I'll put that in the 24 category. 12 times 3 is 36, so I'll put that in the 36 category. And 1 times 13 is 13, so I put that in that category. You also could put, depending upon how you did it, you could also arrange these categories in order from smallest to biggest or biggest to smallest. So a whole number is a multiple of its factors. Thinking of factors then, I have 4 gardens in my yard. In my first garden, I have 30 tomatoes. In my second garden, I have 23 cucumbers. My third garden, I have 15 squash. In my fourth garden, I have 19 carrots. What are the possible ways I could arrange the vegetables in each individual garden so that I create a rectangle or square-shaped garden? Take a moment to write down some ideas for each of my gardens. My tomato plants could have the following dimensions: 1 times 30, 2 times 15, 3 times 10, and 5 times 6. I also know that 30 times 1, 15 times 2, 10 times 3, and 6 times 5 are all the same, so I do not need to write them that way or write them twice. For my squash, I could have 1 times 15 or 3 times 5. So 1 row of 15, 3 rows of 5. My cucumbers, though, I could only create 1 row of 23 or 23 rows of 1, which would produce the exact same pattern. Similarly, my carrots, I can only do 1 row of 19 or 19 rows of 1. That's interesting. Prime numbers are whole numbers greater than 1, that have only one set of factor pairs. Composite numbers are whole numbers that have more than one set of factor pairs. So my tomato and squash plants would be considered composite numbers, whereas my cucumber and carrots would be prime numbers. Helen raised $12 for the food bank last year, and she raised 6 times as much money this year. How much money did she raise this year? Sandra raised $15 for the PTA, and Nita raised $45. How many times as much money did Nita raise as compared to Sandra? Louie raised $45 for the animal shelter, which was 3 times as much money as Anthony raised. How much money did Anthony raise? We're going to use tape diagrams to show these relationships individually. So let's start with Helen. Helen raised $12 for the food bank last year, and she raised 6 times as much money this year. How much money did she raise this year? So last year she raised $12. We want to know how much she raised this year, knowing that it was 6 times as much. So I'm going to rewrite 12 6 times, so 6. So altogether, Helen raised $72 this year by adding them all together. Sandra raised $15 for the PTA, and Nita raised $45. How many times as much money did Nita raise as compared to Sandra? So the money that Sandra raised was $15. We know that Nita raised 45 altogether. But how many of those 15 will fit into the total of 45? Well, we would need 3 copies of 15 to reach $45. Therefore, Nita raised 3 times as much money as Sandra. And then Louie. Louie raised $45 for the animal shelter. This was 3 times as much money as Anthony raised. How much money did Anthony raise? We're not sure how much money Anthony raised, but we do know that Louie raised 3 times or 3 copies of how many to get $45. 3 copies of what gives us $45? Well, I know that 15 times 3 is 45. Therefore, Anthony raised $15. Let's make a list of the first 10 multiples of 3. 3, 6, 9, 12, 15, 18, 21, 23, 27, 30. And we did this by skip counting or counting on our fingers. Which of the numbers in our list are also multiples of 6? What pattern do you see in where the multiples of 6 appear in the list? So I rewrote the list and I highlighted the multiples of 6. 6, 12, 18, 24, 27, and 30. I see that every other number is a multiple of 6 within my multiple of 3. Which numbers in the list are multiples of 7? Can you predict when multiples of 7 will appear in the list of multiples of 3? Explain your reasoning. So here's my multiple of 3's again. Again, the 6's are highlighted, and then I super highlighted 21, which is a multiple of 7. The first multiple of 7 appears after the 7th number in the sequence. We might guess that it may happen every 7th number. We could also check by extending our list of multiples of 3 and working our way through them. When looking at the multiplication chart from 1 to 9, which numbers appear only once in the table of products? Where are these numbers located in the table? Why do you suppose that's true? Which numbers appear the most frequently in the table and why? And which numbers between 10 and 20 do not appear in the table? What do these numbers have in common? So I've highlighted the numbers that only happen one time. The numbers are 1, 25, 49, 64, and 81. These numbers only happen one time. These numbers make sense because a number such as 48, which is 6 times 8, which is not on the diagonal, also appears as 8 times 6. This is the commutative property of multiplication, and several of these squares happen. The ones highlighted in this next table represent the most frequently that appear in the table. These are numbers such as 9, 16, 36, which appear 3 times. The numbers which appear 4 times have 2 distinct factorizations into single-digit numbers. For example, 24 equals 4 times 6, which equals 3 times 8. If the table were continued further, other larger numbers such as 72 and 48 would appear way more than 4 times, since the number 72 will eventually appear 12 times and the number 48 will eventually appear 10 times. Which numbers between 10 and 20 do not appear in the table? What do these numbers have in common? So I wrote all the numbers between 10 and 20, and I see the only numbers that do not appear are 11, 13, 17, and 19. These would be considered prime numbers, which means that 1 times 11 is 11, and 11 times 1 is, and I don't see that 11 as an option, 13, 17, or 19. Mrs. Cookie sends cupcakes all over the world. Last month, Mrs. Cookie shipped 525 cupcakes to her customers. This month, she shipped 5 times as many cupcakes as she did last month. How many cupcakes did Mrs. Cookie ship this month? Let's use an area model to represent 525 times 5. Well, I know that 525 can be decomposed into 500 plus 20 plus 5 into its place values. So then I can take 5 times 500, which is 2,500, 5 times 20, which is 100, and 5 times 5, which is 25. Adding them all together, I see that it would be 2,625 cupcakes that she shipped this month. Notice that we decompose the numbers, and then I use the distributive property to share 5 amongst all of them. Another way we could do this is decompose pieces of the numbers. So I know that 5 can be written as 2 plus 3, and I can rewrite 525 as 500 plus 25. Well, then I can create an area model with 3 and 2 on the left and 525 along the top, representing the two numbers that we added together. So then in each box I can fill in 2 times 500 is 1,000, 2 times 25 is 50, 3 times 500 is 1,500, and 3 times 25 is 75. Adding all of these pieces together, 1,000 plus 1,500 plus 50 plus 75 gives me 2,625 cupcakes. We decompose both numbers into more friendly numbers. However, either way, we use the distributive property to multiply the decomposed numbers together. So whether or not we did it just decomposing 525 by itself or both of them, we still get the same result. We can use different strategies to solve the same problem and still get the same answer. Prime and composite numbers are now a new way in which we can classify whole numbers. Sort the numbers into the two categories of prime and composite. Use counters if you need to see equal rows and columns. Take a moment to pause the video and classify the numbers. The only prime number in our list is 2. The others are composite. Some examples, 3 times 9 is 27, 3 times 31 is 93, 2 times 17 is 34, and 7 times 7 is 49. The table below shows a list of numbers. For every number listed in the table, multiply it by 2 and then add 1. Record the result on the right. Go ahead, pause the video, take a moment to double the number and add 1 to each number on the left, and then we'll go over them and talk about some things that we might see. So the first few I did for us wrote out the expanded form of them. So each one is multiplied by 2, and then to that result we add 1. And you'll notice that we end up with 1, 3, 5, 7, 9, 11, 21, 47, 115, 201, and 619. What are some things that you might notice about the numbers in the table? Well, one student noticed that all the numbers are odd. I also noticed that all the numbers were a difference of 2 between each one. But does an even number multiplied by 2 result in an even or odd number? Well, if we have an even number and we multiply it by 2, the result will always be an even number, because multiplying by 2 doubles the number of objects we have. So as a result, all of our objects started with a partner, and now we'll continue to have a partner when we just double the amount that we have. Does an odd number multiplied by 2 result in an even or an odd number? Well, when we start with an odd number, it will also result in an even number. Because we start with an odd number of objects, not everybody has a partner. But as soon as we double the amount that we have, soon that last piece that did not have a partner will now have a partner and everyone will have a match, therefore giving us an even number. Does an even number plus 1 result in an even or an odd number? Well, an even number plus 1 will always be odd. Because there are an even number of objects, each piece will have a partner. However, if we add one more of those objects, there's going to be one left over that won't have a partner. Does an odd number plus 1 result in an even or an odd number? Well, an odd number plus 1 will always be even. If we start with an odd number of objects and there's one left over without a partner, if we add one more piece in, then that odd one will automatically now have a partner to pair up with, so every object will then be paired up. So going back to our original part, explain why all the numbers we entered in the table were odd. Well, we can use some of the understanding that we had from the previous questions to conclude that the values in the right column are all odd because we first multiplied either an odd or an even number by 2, and we just discussed that no matter if we start with an odd or an even, when we multiply by 2, the result is always an even number. But then we're adding 1, and we decided that an even number added 1 to it will always be odd. We further can write the generic form of that pattern. No matter which number we choose, n, we'll just call it the generic n. The pattern we did was take 2 times whatever number that was in the sequence and then added 1 to it. Moving on to operations in base 10, there's a lot of things happening here. We're still going to add, subtract, multiply, and divide. We're going to take it a step further than we did in 3rd grade. So let's start with an input and an output table. I want to know, how do we get from the input to the output? What is the operation that we're doing? So they have an example there for us. So how do I go from 6 to 60? Well, it looks like we multiply by 10. So I can fill in the chart. 12 times 10 is 120. 25 times 10 is 250. And then I ask, what times 10 is 320? And what times 10 is 470? So we can fill in the chart. Let's take this chart one step further and repeat the result. So 2 times 10 is 20. 20 times 10 is also 200. So I can finish filling out my chart as 1200, 2500, 3200, and 4700. I see that by multiplying by 10, we are shifting our digits. We also know that the value of a digit depends on its place value. But what happens if we shift to the left? So I see that going from 12 to 120, I'm shifting my pieces to the left. So my tens goes to the hundreds, my ones goes to the tens, and then I use 0 as a placeholder. So 110 times 10 gives me 100. 10 times 10 is 100, and 2 ones times 10 is 2 tens, so 2 times 10 is 20. Further, if I shift it left and then left again, so notice that we go to the thousands, the hundreds, the tens, and we keep going and adding a 0 for a placeholder. How does the value of the digit in the tens place change when the number 53 is shifted to the left? Support your thinking using an equation. Pause the video, take a moment to try to see if you can write this out yourself, and then we'll talk about it. So I know that 50, when I decompose 53 into 50 and 3, they're multiplied by 10. Each part, so 50 times 10 plus 30 times 10 gives me 500 plus 30, so 530. Notice when it's shifted to the left, 53 becomes 530 when I take 53 times 10. Let's say we have the following representations of numbers. How can we sort these representations? So I see I have an assorted ways that I can write a bunch of different numbers. I'd like you to fill out the table using standard form, word form, expanded form, and base 10 representations. Pause the video, sort these out, and then we'll talk about them. So written in standard form, we should have 421 and 214. The word form, expanded form, and base 10 pieces. This may not have been the original way when presented this problem you would have sorted. Rather, my first inclination is to sort them out based on which number they represent. So writing 421 using numbers, expanded form, and the written word, 223 using the standard form, written form, and base 10 pieces. But it doesn't matter the way we represent using the different forms. Changing how it is written does not change its value. Equivalent numbers have the same value no matter how they are written or represented, just as we saw in the previous slides. Pause the video and fill in the missing information, written in numeral form, expanded form, and base 10 blocks. Part A, we should get 2067. Part B, we should get 800 plus 40 plus 3. Part C, we need a flat and a long, or a 1 100 piece and 1 tens piece. A friend asks you to check their homework to decide if the answers were correct or not. Thinking about when rounding to the nearest 10, what is the smallest whole number that will round to 100? Your friend answered 90. What is the largest whole number that will round to 100? Your friend chose 104. How many different whole numbers will round to 100? Your friend chose 5. Stop the video, determine if A, B, or C are true or false. Part A is incorrect. The whole numbers which would round to 100 would include 95, 96, 97, 98, 99, 100, 101, 102, 103, and 104. Those are all the numbers that would round to 100 when rounding to the nearest 10. Therefore, the smallest is 95. Part B is correct. Looking at the numbers listed above, the largest is 104. Letter C is incorrect. Looking at the list above, we see there are 10 possibilities, not just 5. During a competition, you can jump rope 234 times. Your 5 teammates also jumped rope about the same amount. Estimate how many total times your team jumped rope. We're going to use estimation. So I'm going to look at 234 and I'm going to round to the nearest 100. I see that 200 is closest to 234 when rounding to the nearest 100. I'm going to take 6 and round it to 10. So I could estimate this as 200 times 10, which is 2,000. I could also take this as 200 times 6 itself, since that is easy enough to multiply for that 1,200. Similarly, I could take 234 and multiply by 10 and get 2,340. Again, these are all estimations depending upon how you're rounding. Let's round to the nearest tens. Let's say I round 234 to the nearest 10, which would be 230. I could then round 6 to the nearest tens, which would be 10 itself, for 2,300. It's very interesting to see that depending upon how we round depends upon the estimation that we find. Rollo has 159 pennies and Zeus has 1,431 pennies for a fundraiser. Zeus is excited to share about how many times more pennies he has compared to Rollo. Zeus says, I collected 10 times more pennies than you. Rollo says, no, only 5 times more. Explain the estimation strategy that Zeus and Rollo each used and argue which way makes the most sense mathematically. Let's take a look at Rollo's estimation. It looks like Rollo rounded to the nearest 100, so 159 would round to 200, and 1,431 would round to 1,000. 200 times what would give us 1,000? So 200 times 5 is about 1,000. That's how Rollo got the 5 times more. Let's look at Zeus's estimation. Zeus estimated that 159 is closest to 150 when rounding to the nearest 10. He also rounded 1,431 to the nearest 100 as well for 1,500. So he asked 150 times what gives us 1,500. Easy enough to mental calculate that 150 times 10 is 1,500. Again, Rollo and Zeus rounded differently, so the number of times they get is also different. Not necessarily wrong, but just different. Let's use a tape diagram to find the exact answer. Zeus's pennies were 1,431. Rollo's were 159. I need to know how many orange can fit onto the blue bar. I see that 159 will fit on the blue bar 9 times. So 159 pennies times 9 is 1,431 pennies. So when I put their estimations next to each other, although both strategies are correct, Zeus's strategy on the right here of rounding to smaller place value makes more sense mathematically because his estimation is closer to the actual answer. Number lines are an effective tool when rounding numbers to any place value amount. Recording benchmark numbers based on place value on number lines helps show which numbers are closer to one another. We know that deciding which place value to round to is an important part of estimation. In third grade, we frequently decompose number to quickly add or subtract numbers together, such as adding 24 plus 46. Here are some possible strategies we have used. I added the 20 and the 40 to get 60. Since 4 plus 6 is 10, I added 10 to 60 to get 70. I decomposed 46 to 40 and 6. I added 24 and 6 to get 30. Last, I added 40 and 30 to get 70. I started with 24, then counted up 4 tens to 64, and added 6 more to 70. Let's extend our ideas of addition to add 147 plus 213 plus 26. Notice there are 2 different students who did 2 different things. How are these the same and how are they different? One may look more traditional to us than the other. They are alike in that they both add like place values. They are different in that one is recorded horizontally and one is recorded vertically. Also, one includes regrouping 10 ones into 1 10. Let's extend our ideas into addition and show how this strategy works with base 10 pieces. Here I have our base 10 blocks using one of our interactive virtual manipulatives. So I need to start with 147. 1, 2, 3, 4, 5, 6, 7. I need to add 213. And I need to add 20. I see that in my ones column, I have a bunch of tens that I could gather up to regroup into tens. I'm going to do that. And I have 1, 2, 3, 4, 5, 6, 7, 8. So I don't have enough to regroup my tens to 100. So overall, I have 386 pieces. Would you believe there is yet another strategy we could use called partial sums to add? So let's add 147 to 13 plus 26 using partial sums. When I add 7 plus 3 plus 6, I get 16. Notice I did not carry the 1 where we typically would carry in our traditional algorithm. Then I move to my tens. 40 plus 10 plus 20 gives me 70. And now I move to my hundreds category. 100 plus 200 is 300. Now I can add vertically. 386. Let's compare 2,135 plus 462 using partial sums and the standard algorithm. On the left, we will use partial sums, and on the right, we will use the standard algorithm. So our first step with partial sums is that we want to add 5 plus 2, which is 7. Similarly, the standard algorithm is the same. We start on the far right. Now, with the partial sums, I'm going to move to my tens category. I will add 30 plus 70, which is 100. Now, using the standard algorithm, 3 plus 7 is 10, so I have the 0 and I carry the 1. Now I will move to my hundreds category. 100 plus 600 is 700. However, with the standard algorithm, I add 6 plus 1 plus the 1 we carried, which is 8. Finally, with partial sums, I will add the thousands. 2,000 plus 4,000 is 6,000, and 4 plus 2 is 6. Now that I have them all labeled on the partial sums, I can add straight down, giving me 6,807. Although it seems like many steps, it still gets us the same place. Match each number sentence to the student's verbal explanation of 155 minus 68. Take a moment to draw arrows to the correct one. Michael added to get the answer. His would be 68 plus how many gives me 155. Danielle decomposed 155 and 68, then he subtracted the decomposed numbers. And finally, Alexa counted backwards from 155 until she found the correct solution. Two students solved 234 minus 145 differently. On the left, you will see the student decomposed her numbers, regrouped them, and subtracted, whereas the student on the right regrouped as needed and subtracted using the standard algorithm. So let's use base 10 pieces to show how this is completed. We know what we know about place value allows us to subtract efficiently, and what we know about whole numbers can be decomposed as a strategy for subtracting and yet still retain their value. Let's review how we use our base 10 pieces. Start with 234. Need to subtract 145. I don't have enough ones, so I'm going to take one of my tens and regroup it to a bunch of ones. Now I can take away 3, 4, 5. I can take away 5 ones. I also need to take away 40 tens or 4 tens. I don't have enough, so I need to regroup one of my hundreds into 10 tens. So now I can take away 40. 1, 2, 3, 4. And I still need to take away 100. So I'm left with 89. Let's solve 326 minus 247 using base 10 pieces to show the steps of the standard algorithm. Take a moment to use your own base 10 pieces to follow the steps. Pause the video and we'll talk about it. You found that you didn't have enough ones in 326 to take away 7 ones. So you borrowed 1 from 2, giving us 10 ones, so 16 minus 7, which is 9. Now we only had 1 10 left over, which I need to subtract 4 from. I don't have enough, so we would borrow 1 from the hundreds, leaving me 2 hundreds, and now I have 11 tens, and 11 tens minus 4 tens is 7. Finally, 2 minus 2 would give us 0, so 79. Now we're going to focus on multiplication. So we're going to use the chart to build an array representing how many pounds of fish each animal eats each day. Arrays are very helpful for us in a multiple of different ways. So we're going to use arrays not only when we use with whole numbers, when we tackle fractions, even when we tackle decimals. They're very helpful in a variety of different ways for students to see how things work. So we have aquarium animals here on the left. We have the amount of animals that we have of each type in the middle, and then how much fish they eat. So let's focus on the emperor penguin. If we have 4 penguins and they each eat 11 pounds of fish, we need to determine how many total pounds of fish we need. So we need 4 times 11. So I've got my base 10 pieces here. We're going to make 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 1 row, so there's for 1 penguin. 2, 4, 5, 6, 7, 8, 9, 10, 11. Or there's 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And there's 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we could then individually count them, or this particular interactive manipulative counts them for us as we go. But it might be nicer if instead of using just individual units, that perhaps we decide that we'd like to use 10 pieces. So we need 4 rows of 11, so 10, 11. So there's for 1 penguin, 2 penguins, 3 penguins, and 4 penguins. So we get the same number. And notice that we have it kind of in 2 separate categories. We've got the long pieces, so the tens, and then we have the units. So if I were to have rotated our picture to the left a little bit, we had 4 rows and we had a long and a unit for each row. So I had a row of 10 and then a unit. So if we were to think about breaking down 11 into tens and ones, we would essentially take 4 times 10 to get 40, 4 times 1 to get 4. Adding those pieces together, we would get 40 plus 4, which is 44. So we have a more abstract array here versus using the base 10 pieces for a visual effect. Now if I look at the bottlenose dolphins, there's 5 of them by 27. Well, instead of using 27 individual units, we might want to use 10, 20, 1, 2, 3, 4, 5, 6, 7. And I'm sorry, I wish these could rotate so that they would be in a rectangle going left and right instead of up and down. But there's for one dolphin. Yep, dolphin. We have 5 of them. 1, 2, so there's for 2, 3, 4, 5. So then we just need to fill in our units, 7 more. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, and 7. Three, 4, 5, 6, and 7. So notice it creates a rectangle. We would then be able to count our pieces, or that there are 135 units altogether, so we need 135 pounds. So think of this, if I were to rotate it this way, kind of make it a little more flat, we would then have the following. So along the left we had 5 dolphins, and along the top I split it into tens and units. So 5 times 20 is 100, and 5 times 7 is 35. So 100 plus 35 is 135. Now our seals, we have 5 seals. They each need 43 pounds of fish. So we would have 5 times 43. So let's break it down using the array. So along the left I would still have 5, and along the top, breaking it down to tens and ones, I would have a section of 10, so 5 times 40 is 200, 5 times 3 is 15, so 200 plus 15 is 215 fish we would need, pounds of fish we would need for the seals. Creating arrays with base 10 blocks helps us think about place value, so we multiply multi-digit numbers more efficiently. We can solve multiplication problems by using place value decomposition and the distributive property. This is also known as partial products. So going back here, we split up 43 into 40 and 3. So notice in the traditional sense of using the distributive property, I took 5 times 40 and 5 times 3. So I shared my 5 amongst 40 and 3. The Pavilion Zoo has reprinted their maps. There are 7 stands throughout the park, and each stand holds 648 maps. Use the area model to determine how many they need to be printed to fill all the stands. So I took 648 and I'm multiplying it by 7. So what I did was decompose my hundreds, my tens, and my ones. So we'll have a hundreds, tens, and ones category. So just if I were to use our pieces, we would have 1, 2, 3, 4, 5, 6, and 40, 1, 2, 3, 4, and then 8 ones. We'd have these all lined up. So we'd have a group of hundreds, a group of tens, and a group of ones. So that's why I have partitioned into 3 separate areas. So then we can use the distributive portion. Well, I have 7 times 600, so 7 times 600 is 4,200. 7 times 40 is 280, and 7 times 8 is 56. Using a little bit of mental math, when I add these pieces together, I see that we would need 4,536 maps to fill all of the stands. There are 23 geckos, and each gecko eats 21 crickets per day. How many crickets are needed each day? Build an array to show your work. So I'm going to have 23 times 21 here. So to build this, if we think, we'll have 20 across the top plus 1, 20 across the side plus 3, but you could have it reversed as well. So let's see what this might look like if I were to have this in base 10 pieces. I changed up our manipulatives just so that I'm able to rotate things a little bit easier using a different manipulative. So feel free to do that along the way here. So use manipulatives that work in our favor here. So we have 21 times 23. So I'm just going to build what 21 looks like. Here's 21. And then we'll build over on this side 23. 1. It wants to cooperate with us. 2 and 3 here. So now let's actually fill in the box. Well, if I have 10 times 10, well, that's going to give me 100. So I need to fill in my rectangle here. Okay, so now I have this 10 times this 1. So to fill in this piece of the rectangle, I'm going to need some tens pieces. Similarly, down here, I'm going to have 1 times 10, so I'm going to need some tens pieces. Oops, I don't want that one. I want these ones here. So we need to fill in to make a rectangle. Okay. So although these are split apart or partitioned, we can still iterate and put them back together. Further, I have this little piece of my rectangle not filled yet. The only thing that can fit in those spaces are ones. So I've created 4 different areas. I have an area of hundreds, I have an area of tens, another area of tens, and an area of ones. So let's see how that looks like in our array. So in our array, we have the 20 and the 1, so the tens and the ones, 20 and 3, so the tens and the ones, and I separated it into 4 different areas. Remember, we had the area of the hundreds, this was a tens area, and a units area. So it's not drawn to scale, of course, but it does just separate for us. And then we have our different numbers. So 20 times 20 is 400. We certainly had 4 groups of 100. In this little area here, we have 20 times 1. We did have 2 tens there, so it would be 20. Here we created, there was 10 here, a group of 10 here, and each one had 3, so we had 3 times 20, so 60. And then our units was 3 times 1, which is 3. And if we add them all together, we get 483. Use an array to show 39 times 33. So break this up into the tens and the ones and see if you can't do the multiplication using the array model. Pause the video, come back, and we'll talk about it. It doesn't matter if you used 39 on the top or on the left. It doesn't matter, you'd still end up with the same result and the same separations. So I broke up into tens and I broke up into the ones. 30 times 30 is 900 for our hundreds. We would have 2 different groups of tens here. We'd have 30 times 9, so 270. 30 times 3, which is 90. And 9 times 3, which is 27. Using a little bit of mental math, we would see that this would result in 1,287. Use an array to show 141 divided by 3. This time we know the result, and we want to divide it into 3 different groups. So let's trash this. Oops. Move this closer and move some of our pieces out of the way so we can work with them a little better. So let's start with 141. And we want to split this into 3 groups. Well, certainly, I cannot split 100 into 3. I can't make a rectangle out of this. So I'm going to exchange my 100 for 10 longs here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now I've regrouped them. I have 14 different ones. So let's start putting them into groups of 3 and see what we can come up with. So we might have to rotate them. I'm not going to have enough room on my screen. All right. Okay, picking up where we left off, we have 141 divided by 3. We exchanged our hundreds for groups of 10. And so now I'm just lining them up by groups of 3 here to see how many what we can do here to make a rectangle. All right. Okay, so I don't have enough to share equally among 3 again. So what we need to do, maybe we should go this route. Yeah. Sometimes it's like a puzzle, putting all of our different pieces together here. So what I need to do then is exchange these tens for units. So I'm going to take these away and bring out 20 squares. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and I'm going to move my screen over so we can see more. So we're at 15, 16, 17, 18, 19, 20. And don't forget we had that unit from 141, so 21. So notice I've got 3 different groups here, and each group has 10, 20, 30, 40, 1, 2, 3, 4, 5, 6, 7. So 141 divided by 3 is 47. Take a moment to pause the video and see if you can't make 852 and divide it by 4 using an array. You should have been able to create 4 groups of 213, and each group would have 2 hundreds, 110, and 3 units. If we know the deer at the zoo drank all the water in their enclosure in one day. If we know that one deer drinks 6 quarts of water a day and the tank holds 390 quarts, how many deer are in the enclosure? Use partial quotients to solve. So I'm going to set this up just like a regular division, long division, but I'm going to do it a little differently than we're used to. So I'm going to think, how many tens can I make with 6 times how many tens gives me the biggest number I can have? Well, 6 times 60 would give me 360. If I did 6 times 70, I would end up with 420, so too many. So 6 times 60 gives me 360. When I take 390 and subtract 360, I'm left with 30. I know that 6 times 5 is 30, so 30 minus 30 gives me 0. Well, then how do I know how many times 6 can go into 390? Well, I take the pieces that I multiplied 6 by, 60 and 5, and I add them together to get 65. A woodpecker is being studied. They recorded the woodpecker for 8 seconds and heard 152 times that it pecked. Assume it pecked the same number of times each second. How many times per second did the woodpecker peck? Solve using partial quotients. So I set this up using long division, and I asked myself 8 times how many tens will get me as close as possible to 152. Well, 8 times 10 itself. If I did 8 times 20, I would get 160. That would be too many. So 8 times 10 is 80. When I subtract 80, I get 72. I also know that 8 times 9 is 72. So when I subtract, I have 0 remainder. So to figure out how many times that it can go in, I add the 10 plus the 9 and I get 19. 370 students signed up this year to participate in a job. The zoo creates the same number of students for each of the 4 days. Will each student have a job? If not, how many will not have a job? Let's use partial quotients. So I'm going to take 4 times 10, which is 40. I can keep going. 4 times 20, 4 times 30, and here I see that 4 times 90 would give me 360, the closest that we can reach to 370. When I subtract, I get 10. I know that 4 times 2 gives me 8, so when I subtract 8, I have a remainder of 2. Our solution then would be 90 and 2, so 92. However, I have that remaining of 2. So the remainder can mean many things depending upon the context of the problem. Here the remainder indicates that there will be 2 students who will not have a job. Let's change the context of the same division problem. There are 300 students coming on a canoeing trip. Each canoe holds 4 people. How many canoes will be needed for everyone to participate? So when I look at this, I have the same division. That part didn't change, except the 2 represents how many people will not be able to fit into the canoe. So therefore, there's 2 students left out without a canoe, which means that we would need 93 canoes so that all students could participate. Now we know that each canoe wouldn't have an equal number of students, but at least everybody would be able to participate. Changing the context again of the same problem. Zookeepers are visiting 4 of the local schools today. While they're going to hand out free balloons. They have 370 balloons and want to give the same amount to each school. How many will they hand out at each school? Well, they only can hand out 92 balloons to each school. Yes, there'd be 2 balloons left over. However, that's not enough to give another round of balloons to each school, since there'd be 2 schools that would not have the same amount as the others.